Today on the show is Dr. Liz Whitney. Very special episode for me. Liz is a good friend of mine. When I started doing the podcasts, I have always been fascinated. We've had podcast-like discussions about her research, and she finally agreed to come onto the show and discuss it. And so she's recently completed her PhD at the University of Delaware, analyzing how carbon moves through coastal environments and how we can understand them. Before completing her PhD, she also did very interesting research on forever chemicals and heavy metal contamination detection. So we also get to talk about that. But in the conversation, we dive deep into the coastal dynamics of carbon in forested areas, in agricultural areas, and in urban environments, what that says about how the environment is changing, how the climate is changing. We also get into a discussion about a real-world application of the research and the economics of running a lab and how there are shortcomings in the environment as a whole with education and the economics of running a lab, especially in this political environment, that have lasting impacts on the rest of the industry. All things that I expand on in my articles and my newsletters that you can sign up for at earthonward.com. Thank you always to our partners, Clean Tech Growth Lab. If you're looking to grow in the clean tech space, they are the experts. They're also wonderful people. And if you're looking to grow in any other industry, anywhere in the world, you want to go with Craze and Friends. That is the producer of this podcast. So thank you to them. And now for Dr. Liz Whitney. Dr. Liz Whitney, welcome.
Happy to be here. It's good to see you, Blake.
I just want to recognize for everyone that will ever listen to this, it was a very special moment for me to be able to address Liz as a doctor, because we've known each other for a long time, and it's something she's been talking about for a long time, and a huge accomplishment. So shout out to you for that. There's a lot more that I could say about the work that you have done, that you do, who you are. But before we get into all of that, if you could give a brief introduction of yourself and what you're building.
Yeah. I'm Dr. Liz Whitney, and I recently completed my PhD, so that's why the doctor is such a big deal. But I consider myself to be a biogeochemist, and I study how carbon moves in coastal environments to understand how climate change is impacting our natural and our built environments.
So that touches a very special place in my heart, something that we will talk more about. But that biogeochem aspect of Liz's career is actually where we met. We took a class in college together around that. And she obviously took it much further than I ever did about understanding those core concepts. So I'm sure this will be educational for me, just like that course was. And something that I think is really impressive about what you've done, and something that I want to elaborate on, is just that. So in the clean tech, the climate tech space, there's a lot of attention around funders, around founders. There's obviously talk about policy and policymakers, but less so do I see a lot of attention around researchers or research. I just think it's less shiny. There's not like this allure where it's like, oh, money, VC investment, stuff like that. That stuff is important, but academic research and research in general is also a really important arm of the entire ecosystem. And so could you talk a little bit about how you got to where you're at, being a postdoc? You could start, I think, where you first realized that there's an interest in chemistry for you, and just a little bit about your journey to now.
Well, if we're starting with my love for chemistry, we're going all the way back to elementary school, because I have always loved learning. And one thing that's really fun about chemistry is that it's a very visual science. There are parts of other sciences that are really visual too. Like we've got in biology what we call charismatic megafauna, that are these like animals that people can get really attached to and really love. What I love about chemistry is that you can mix two things together and see a reaction happening right before your eyes. So even as a kid, that's something that I was always really drawn to. And I ended up going to college with Blake, and studying chemistry and really enjoying the research aspect. Getting to learn hands-on is much more exciting than just sitting in a class and taking notes and doing rote memorization. So I really love the laboratory research aspect of things. But in terms of getting towards the biogeochemistry side, as a part of my major, I got to take this biogeochemistry elective. And that class was so incredible because we got to go to Panama for 2 weeks and we did field work there. And that is where I realized that I could combine this love that I have for doing science and having this hands-on learning with my love for also being outside, because I was studying chemistry before in the lab in a basement with no windows. I didn't really know or have exposure to the life of field work. And that is where I really was driven to pursue a PhD, to continue to learn, continue to do that research. But ultimately I ended up choosing the field of biogeochemistry because I got to go outside too. So that's a little bit of how I ended up there. While I was in grad school, though, I realized that the academic world, you talk about how it's really important, but also how it's not this like bright, shiny thing. I think it's a world that's very insular and very isolating. And I think that goes all the way back to the history of like how academics started. Scholars were very wealthy, and there's this barrier between doing the highest degree you possibly can and the rest of the world. So yes, academic research is very important, but I think that it's also so necessary that we start to shift the narrative that science is elite always, because we can't solve the problems that we have today without everyone's voices. And so that's something that I'm really driven to moving forward in my career, is making sure that everybody has a voice at the table, because especially in the climate space, there are so many other intersectional issues that impact climate change, that are impacted by climate change, and bringing those spaces all together is kind of, I think, somewhere that we can move forward and hopefully make positive changes.
Yeah. Wow. I usually try to bring that type of energy around, towards the end of the episode, but we're just bringing it now. So I bring everyone together. There's two things first. Three things. You said charismatic megafauna, and that is a term I've never heard in my life, and I love that. Applies to many people, many things in my life. I don't know if that's the way to interpret it as a non-chemist, but that is a hilarious term to me. Two, would like to thank Professor Dave Gillikin for that class, Biogeochem, where we met. And then third, before we get into the main bulk of the research that you ended up doing in your PhD, you were contributing to some interesting environmental chemistry research at Union, right?
Yeah, I worked on 2 projects there. Do you want me to talk a little bit about them?
Absolutely.
So the first project I worked on was understanding how to use naturally occurring clay materials to remove PFAS, or perfluoroalkyl substances, that I'm sure a lot of people are really familiar now with that term. These are the forever chemicals that stay in the environment forever. They don't like to break down. And we use granulated activated carbon filtration systems a lot of the times, but once those filters are full, they have to get thrown out. So we were using these naturally occurring clay materials that we could regenerate after collecting or removing PFAS from water. We could remove the PFAS from the filter and dispose of it in a different way, in an appropriate way, rather than right down our drains, and then use them again. And we had a pretty good return rate of reuse on those filters,
Sure.
which was really interesting. Go ahead.
So was that the you said there were two? So was that one of them?
Yep, that was the first project I started and where I really got bitten by the laboratory bug.
Okay.
And then the second project I worked on was using, give me a second. This is what I did my senior thesis on, but what big. So this was a physical chemistry project, and we were using gold nanoparticles on the substrate to try and create these nanosheets, these really small 5-micron sheets that could be used as sensors to increase the reaction, basically increase the signal of heavy metals in water. So the idea here would be to take these sensors, put them in places where lead contamination is known or other types of chemical contamination, and be able to pick up these signals faster than if we had to go out and collect a water sample, bring it back to the lab, and figure out how much was in the water at that time. So those were two really groundbreaking and interesting studies that are still continuing today.
Wow, well done. Yeah, I had no idea about that second one, and so the way that you, I was like really focusing while you were explaining that, because and I think you did a really great job synthesizing that. So thank you for
Thanks.
for my ears for making
It's
that
been a really long
understandable.
time since I've thought about those. So
Well, you did that was cool. So before we get into the biogeochem space, had you always set out to do work or think about the climate, the environment, these types of things, or is it something that you just fell into?
yeah, I've been really passionate about the environment my whole life. It probably started with some school video on recycling or something, and I came home and I was like, we have to recycle. Nature is all we have, and we have to protect it. And that doesn't mean that I think that everything people do is bad. I don't think that's true at all. I think that we can heal nature just like nature can heal us. But I've always been really driven towards that protection of the environment. And as I've grown in my studies and in my career, I've realized that I care a lot about protecting communities as well. So those are interconnected, as I said before, and hopefully we can, use those two things together, ecosystems and communities, to protect ourselves and the environment in a harmonious way.
That's it. So that's that. That touches on my follow up to that, which was, so for me, what you mentioned was recycling, and I think I would. I mean, I don't know if you asked me 7 years ago, Blake, what do you want to do? And I say, oh, I want to save the planet. I want to do something sustainable. I want to do something environmental. But my first introduction to that whole world, that system of thinking, was recycling. And that was the first thing that I got passionate about. I was like, wow, this is something that could be done a lot better than it is. And that's the first thing I got excited about. And then the more that I learned about it, the less excited I became about it, because I understood how complex it was. And this excitement and optimism had to be grounded in reality about not only what was currently happening, but why it was currently happening and what it took to change it. And so clearly, because we're on this podcast together right now, I'm still very passionate about clean tech, climate tech. It's just has changed and taken a totally different form than it was in the past. And so how has your passion, your love for nature and these things. I mean, you mentioned a little bit of it. It's changed to more of, hey, this is communities too. But how has it changed over time? The more that you've learned about, the deeper you've gotten into your field of research, or the more you've learned about how the world works. How has that love or that drive changed?
I think that's a really great question because we are living in a really challenging time. We're faced with just these massive and seemingly insurmountable issues. And the more I've learned about some of these issues, the more frustrating it can be to keep going because they feel so big and there are a lot of systems in place that are preventing us from solving these problems. But I'm not alone. There are teams of scientists and policymakers and researchers and funders and founders and all of these incredibly talented and smart people who are also driven. So that drive, knowing that there are people who care, is what keeps me going because it feels so big and it can be really difficult to kind of push past that. But why would we give up for something that we care about just because it seems difficult? It's a roller coaster every day sometimes, especially in the political climate that we live in right now. But I'm not going to give up because there's too much at risk and there's too much good that will come out of pushing through.
Yeah. Nice. Shout out to these that I mean, not in the way that you referenced it before, but that sounds like a nice shout out to the community that you're inside of, that elevates you.
Absolutely.
So then now I would like a little bit of a lecture almost because I'm excited to learn. In the the years that you were doing your PhD research, could you first succinctly describe what your PhD research was about?
Yeah, so I studied the climate change effects of sea level rise and ocean acidification on how carbon moves in coastal environments adjacent to forests, agriculture fields, and the urban environment.
How is it that your research attacked those three different those environments? Because you had said forests, you had said near agriculture, and you said urban environments. Those are the three. So those seem like extremely different places, and with extremely different inputs and outputs, and real world context. So how is it that you attacked all three of those places?
Well, we went back to the fundamentals of the scientific method, so we used the same methods in every location, and that was the point of choosing those types of locations, is that there hasn't been a comparison previously on those types of environments, specifically looking at how the dissolved organic matter or the main aquatic form of carbon is moving in these environments as sea level rise is increasing. And the importance of looking at these different land types and land uses is that I went to school at the University of Delaware, which is located in the mid-Atlantic of the United States. And that region is experiencing relative sea level rise at much higher levels than the rest of the globe. So not only were we interested in understanding how are these land types different from each other, but we were also really interested in how are these land types changing over time as a result of these climate change issues.
How is it that you were these samples that were collected physically? Were these extracted from existing data sets?
So
Both?
I had this incredible team working with me from the University of Maryland, and they had these automatic water samplers called ISCOs. Don't ask me what that stands for. I think it's just a brand. We could program these water samplers to collect water samples whenever we wanted. So we had ours programmed to collect samples at 6 different sites across the same 24-hour period. And then our team would collect the samples, they would bring them back to the lab and then filter and acidify them to make sure that we were just looking at the dissolved organic matter portion that we were interested in. And that was the point. The filtration and the acidification achieves those things because dissolved organic matter is really complex. And then they would ship the samples to me, or in some cases we would work on processing the samples together. But this is the part that is like, it seems really complicated on the outside, and if I use the big scientific jargon, it would feel overwhelming, but I've got a really fun analogy.
Yeah, do it.
So I like to think of myself like an interviewer for water.
Okay.
So I was interested in understanding what the carbon was made up of, because it's not just carbon. There's dissolved phosphorus, nitrogen, and sulfur as well in these compounds. And so I would run these samples on 4 different instruments, and each instrument was like me asking that sample a different question. So I used a total organic carbon analyzer to figure out the amount of carbon in each sample. I did spectroscopy to understand where that carbon was coming from, because seeing the absorbent signal of these photoreactive chemicals can tell us if the carbon was coming from the ocean or from the land, or if it was a mix of both. We used fluorimetry to understand the bulk properties of the part of the organic matter that fluoresces under light. And that could tell us basically structural components. And then I also used size exclusion chromatography, which tells us the size distribution of the molecules that make up the dissolved organic matter.
So to continue suspending this resolution of what you ultimately found, was this the methods that you described and the goal, the questions that you were asking in the interview, just like me to you right now, which is a great analogy. Is this something that was the same over your 4 years? Is this an ongoing project? Did this change at some point throughout the 4 years?
So that piece of the project was carried on throughout the whole 4 years, and there are still researchers trying to figure out some of those questions, because those methods that we were using have been used in land-based like lakes and rivers with really great success, and they're also used on ocean samples, and just like across the board, those are the gold standard ways of understanding how organic matter is changing. But what's really complex about estuaries and coastal areas is that they are so constantly changing, even more constantly than pretty much anywhere else, because you've got tides coming in and out every day, and that's pulling, when the tide's going out, that's pulling carbon from the land. When the tide's coming back in, that's pushing up carbon from the ocean. And these samples are so, like, you're looking at a snapshot of a 24-hour cycle, trying to understand what's going on. And these samples have so much sediment and particulates that don't necessarily play a role in the carbon cycle, in the organic carbon cycle, that are going to stay stuck in there just because the water's so turbid. So we've got a lot of artifacts that we're dealing with, and it's really hard sometimes to piece out what's actually happening. And we realized over the course of my studies that these methods aren't necessarily usable or
interesting,
as explanatory as they would be for a sample that was coming from a less complex environment.
Ooh, so I guess partial drum roll then. Is that a conclusion that you ended up drawing from this from your PhD research?
Yeah, we were not expecting that. We were really confident that our methods would work, but because the salt levels are changing all the time, it's kind of hard to compare a sample that's coming from low tide that's not very salty to a sample from high tide that is very salty. Those salt levels can alter the way that the chemicals are looking under those different instrumentation methods.
Sure.
So there needs to
Wow.
be some kind of normalization, and I didn't have time to work on that, but that is sort of a big thing to consider.
Wow. Well, that seems, obviously not an ideal conclusion, but that seems like a very impactful and meaningful conclusion from your research, is the fact that, hey, we've spent a lot of these years using this instrumentation to collect the data to ultimately draw some kind of conclusion. And the conclusion that we drew is that this instrumentation is ultimately not ideal for this research. So have you seen, or at least had discussions with anybody else in the similar field about that specifically? Like if you're not using those instruments, then what else is available?
I mean, the thing that's tough is that we're looking at these compounds that we can't actually see. So we have to just continue to do more research to understand these environments as they change and figure out ways to use what we have to keep learning, keep developing our understanding. Like, it's not as simple enough to just say, like, oh, this method that we've been using on these other environments doesn't work. Like, how else do you keep researching?
Yeah.
Like, you can't just develop these new tools that have been in development for decades now. So it's a big challenge. I mean, these instruments are expensive. Their upkeep can be quite painful. And another challenge on top of that is sometimes our instruments are pretty old and they're not supported by the companies that make them anymore, because the companies want to keep growing and have us buy a new instrument, and we can't necessarily afford that. So there are a lot of challenges just from the funding side, and so I think this really points to just we need more research in these areas.
Okay. Yeah. So I made a bookmark because I want to come back to that. But just to close up this segment. So that is, I think, a really interesting conclusion to draw from your research. Were there any other major conclusions that you ended up drawing in your research?
Yeah. So my research was one piece, the biogeochemistry piece, in a whole environment study. So there were conclusions being made about how sea level rise is changing the geomorphology and how the geomorphology is actually impacting the way that sea level rise is changing environments. There was a group that was looking at the ecology and another group looking at the hydrology. And so all of those things impact each other. And the research is still ongoing in all of those areas. So I don't have the major, huge findings to share, unfortunately. But that being said, the driver of organic carbon in the estuaries that we were studying, regardless of the hydrology, regardless of whether it was a forested area or an agricultural field, the driver of the way that carbon moves is going to be the tides or the big storm events that will bring lots of water inland, which isn't a groundbreaking finding. That's pretty well known across the field, but that hadn't been studied directly in the field sites where we were working. So it was exciting to see that we had a finding that corroborated other findings across the globe.
So then, big picture question, and you can take it from the perspective of this instrumentation conclusion, this conclusion that you're speaking to about the directionality and the drivers of the organic carbon in these things. What is the real world impact or real world context of this research project?
So as sea levels rise and water is pushed inward, the salt water that cannot sustain crops or forests, the land is changing. So farmers who have been farming on the coast for generations are no longer able to grow their crops because it's too salty. People who used to go to a certain forest to hunt or do other forms of recreation are seeing that land change from forest to marsh. And that has huge implications for the people who live in these areas. But environmentally speaking, if we're just thinking about this from the perspective of how is the environment doing, these marshes are protecting the upland area from erosion. They're protected from huge storm surges. So the implication of this research is that people's land is changing and we need to understand how to adapt with it, but also the environment is changing as a response to this thing that's happening, and it's doing what it can to protect itself.
Have you had conversations with, again, other people in the same space, or maybe in different, again, commercial spaces or policy spaces that have digested this research and are working on solutions or working on this problem in a particular way that you know of?
Yeah, coastal resilience goes by many different names depending on the location you're in, but coastal areas where the majority of the population across the globe lives, they're all looking at this issue of sea level rise and trying to understand how to protect their communities from major floods with hurricanes or typhoons, how to reinforce their buildings. Insurance companies are taking advantage of this issue and not insuring certain places. So anyone and everyone in urban planning and any kind of urban policy development is thinking about this issue. It's a really big question and problem for a lot of places.
So something that I wanted to talk about also, because you'd mentioned it, is what was your experience? You were working in the lab, but to what extent were you involved with running the lab, as far as getting the equipment serviced, keeping it upkept, dealing with vendors and things like this?
Every lab is run differently, but in my lab, we were all our own lab managers. So if we were running out of supplies, we had to order them ourselves. If an instrument wasn't working, we had to call the manufacturer and see if we can get some support. It was a pretty good experience to learn how to do that type of project management. And organization is really important for keeping yourself moving forward because there was no one else there to do it for you.
Got it. So then, Dr. Liz, tell me about a little bit about the economics of running your lab. And so some of the conversations I've had, and like you said, labs are ran differently, but ultimately there's a lot of similarities between running a company and needing to keep it afloat. Almost just often it's been described as just buying yourself time. Again, in the founder context, it's buying yourself time so that you can find the product market fit that you believe is there, and that will start generating revenue and blah blah blah. But from a lab's perspective, what is the role of revenue? Because there's not really there is production from a lab. There is there is an expected output from the work that's going into it, but it's not the same where I'm sure there's examples of it, but I'm not aware of a lot of them where you're selling your research or you're selling a product in order to fund the lab itself. So what's the relationship between funding and running a lab and dealing with these vendors and, budget cycles and all of these things?
Yeah, so in a more typical time when there's funding for science at the federal level, they will put out these requests these notice of funding opportunities, and then the lab groups will submit proposals and hopefully receive them and sort of buy themselves time, X number of years, usually 3 or 5 years, to do that research with the expected output of one or more journal articles. And that's sort of the return on investment that these funders get, is this research that's done.
Okay.
So it's usually the principal investigator or the laboratory advisor, usually the professor who's running the lab, to look for these opportunities, to apply for them, and work with the students to apply for them. And then it's the student's job at the graduate level typically to carry out that research and make those publications happen.
So you said mostly it's grants and funding from a federal level?
Yep. In a more typical time, that funding has been pretty roughly cut up at this point. So I think the academic world is still reeling from that a little bit and trying to figure out where their money can come from. But an avenue is philanthropy. You know, philanthropists will donate to universities and colleges for buildings and other infrastructure, and hopefully moving forward they can step in and fill some of those funding gaps where the federal government is not funding science right now.
So is that, I mean, would that fall into the same category as grants, though?
Yeah.
Or are they in a different, okay. Are there similar, is the funding body generally NIH? Is that?
It depends on the scientific field of study. NIH is probably the biggest funder of research in the U.S. On the academic side.
Okay.
There's also the National Science Foundation.
Okay.
They're a really big funder for a lot of graduate universities. The National Oceanic and Atmospheric Administration does some grant funding for academic research. Those are NIH and NSF are definitely the biggest ones.
Are there any on the state level that are significant to any degree?
I think that's going to depend on the state. Like the New York State system does a lot of funding for graduate research, but generally speaking, in terms of the revenue that universities are bringing in from grants, it's not going to be as high at the state level, just because a lot of those states are getting their money from the federal government.
I see.
To funnel it through the state to those universities.
Got it. Well, with this then, is there? So where do you see it going? Like, based on your experience in this lab, getting a PhD, you know, the amount of time you spent in these environments, is there? And you know, any ideas welcome. Like, is there some other means of funding science that is that is, you know, deviations away from how things currently are, given the fact that I would assume, you know, in this administration, like there's not, well, I mean, you said it, there's not a lot of money going to science as there once was, and there's a lot of adjustment that's needing to be had. So do you see any alternatives to funding outside of just more grants, more philanthropy, so that there's not as much reliance on federal funding?
I think the way things are right now, we have this cultural shift that has to happen, because there's this idea that graduate school is really pompous and for the elite only, and education is the way out and through a lot of economic challenges for a lot of people, but it's also a barrier. So I really think that we're going to lose a lot of potential students because there is no funding right now. And this is painting a really bleak picture, and I think that we're going to face a lot of challenges in the academic world. The academia is already facing much lower acceptance rates and things like that. So I think that we really just need to, I think there is a funding issue acutely, yes, but I do think that we will get back to funding science in the next few years, hopefully. But I think the bigger issue is going to be, how do we encourage people to continue to apply to these programs when they're not painted in a pretty light?
Sure.
Grad school is hard. It's a huge mental battle. anyone can get a PhD. It's not about smartness, it's about being driven. And probably you're going to complete a PhD out of spite, whether that's to, some person who told you you couldn't do it or yourself. It's tough. It's really hard. But it's not because of how smart I am that I have this degree. It's because of how determined I was just to do it and to prove to myself and the world that I could do it. So I don't think that the funding issue is going to be as long-term of a problem
Gotcha.
as it will, as culturally it is to just, grad students aren't paid that much, but they are the backbone of universities.
Right.
Without them, research doesn't get done. Then the papers don't get published, and so then the grants stop flowing in. So I think it's a cultural shift that has to happen around education and around especially higher education to sort of solve the issues that we'll have moving forward rather than funding.
Well done. That was a really nice way to go. Hey, Blake, yes, funding, and actually, this is it. that was really elegant. That was awesome. So 3 last questions for you. So I'm currently doing a series, and it's highlighting women leaders in science. And so I'm curious if you could detail your experience as a woman in this field, doing the research, and also if there's a younger woman that's listening to this podcast and thinking about going into a hard science field, like you did, applying for grad school, applying for PhD, like you did, like you're saying, what would you say to them?
Wow. I think that anyone can do anything. Truly, I truly believe that anyone is capable of doing whatever they put their minds to. But finding good female mentors is so crucial. Going to a small liberal arts school for undergrad and having this incredible chemistry department that was full of women to the point where they had to hire men for diversity was just this wonderful utopia almost of support. And I definitely took that for granted because when I got to grad school in a male-dominated field, nobody looked down on me directly or said I couldn't do it, but there were definitely discrepancies between the way men and women were treated in the labs, and there were other racial and religious issues as well that I saw other people go through. And so finding mentorship that with people that you can relate to is just, if I didn't have the mentors in my life that I do, I don't know that I would have completed my degree. Because one thing that they told me early on is that you never get over imposter syndrome as a woman. And so far in my experience, that's true. It's a roller coaster of ups and downs and feeling very, very capable some days, and then challenges arise and it's like, well, I'm just a woman. What am I doing here? And that's ridiculous. You're here for a reason. You're capable. But having those women in my life really pulled me through.
Nice. Thank you for that. I think you, my final 2 questions is related to something that you were getting at, but and you can take it from, any perspective, like, you just gave your experience as a woman or this grad application or something completely different, but I'm curious where you're at now and with the work left to be done. What is the biggest hurdle that you're facing at the moment, and how is it also an opportunity?
I think there are 2 hurdles to touch on. Number 1, it's a really tough job market, and there's so much work to be done, but everybody is applying to those jobs right now. But that's an opportunity to get my name out there, see what other avenues I could go down. I've got this kind of non-traditional path going from pure chemistry to being a field scientist and going into the geosciences. So my path is going to go down a different avenue that I didn't think was possible, which is really scary, but also really exciting. And then I think more broadly speaking, sort of big picture, we have this challenge of combating climate change. And I think that's a really exciting challenge to face because we have a lot of solutions and all of these really talented people who are going to work um, on fixing these issues that are arising. So big hurdle, but it's going to be a really big reward as we work through it.
Nice. Well, within all of this, I'm curious, Liz, Dr. Liz, what inspires you?
There's a lot that inspires me. Just being out in nature is really inspiring. Nature is very resilient. Um, Mother Nature will always succeed and come back from whatever people throw at her. But also, communities are really resilient too when they're given the resources and the space to have their voices heard. Um, I'm I am in this position now to hopefully leave the world in a better place for the people who have sort of paved that path for me. So I'm inspired by the people who wanted to have these opportunities and didn't because women didn't go into marine biology 50 years ago. And I'm inspired by the communities who need our help, and hopefully we can give them the voice that they deserve.
Let's go. Let's do it. Well, if anyone else was inspired, because that was very inspiring in itself to follow along with your journey, what's the best way to do that?
You can follow me on LinkedIn or connect with me on LinkedIn. And yeah, I don't have a website or anything, but I'm Elizabeth Whitney on LinkedIn. Follow along to see where I go next.
That's right. That's a web page. That's good enough. There'll be information there. Well, Liz, thank you so much for your time. I enjoyed this conversation so thoroughly. I'm excited to stay in touch and, like you said, see where things go. But seriously, thank you for your perspective on all these things, and I'm looking forward to the next one.
My pleasure.